This conference will now be recorded.
Okay. Yeah, the announcement for recording, right?
Right, sir.
Yeah.
We can begin now.
Yeah, I can. Or I'm just thinking instead of sharing the entire screen, if I can share only the PPT, I mean only one window. That's usually possible. So let me see if that is possible.
Okay, sir.
Yeah, because that make much sense. Yeah, it is available. Application sharing, yeah, it's available. I hope my slides are visible to you, right?
Right.
Okay. Okay. So, good morning to all of you. Good morning for you. Actually, I'm in USA, so it is good evening for me. So today I shall talk about the fundamentals of wire arc additive manufacturing. This lecture is usually goes for a very long period of time because this is my research area as well. And but today I'm going to cover it in two parts. First, I shall discuss about the fundamentals really of the wire arc additive manufacturing. But I believe that some of you, I think, or not many of you, may be already aware of the process and may be interested in the machine tool side of it, like what are the systems available, those has been developed till now, and what all are going to be developed soon. So in these two parts I shall start my presentation. I shall start first with the fundamentals like I mentioned, and then machine tool. But if time does not allow me to cover all of these things, then we shall stop, because I want to give at least 15 minutes for the discussion as well. So Dr. Kailash, can you just confirm my laser pointer is visible?
Yes, sir. It's okay.
Thank you very much. Yeah. So let's start with the history of the metal wire additive manufacturing. Like, since when this really is started happening? When was the first patent which was filed for metal additive manufacturing or metal wire additive manufacturing? So you'll be surprised to know. I should have asked us to make us a wild guess, but I think you will be surprised to know that the first patent of wire arc additive manufacturing was filed in 1920, way back. So you can see these are the few images from that patent, which is written here, the patent number as well. It's a US patent. It says it is a method of making decorative articles that time, but the methodology explained in the patent is exactly same what WARM does nowadays. It deposits the material on a substrate by using a welding gun, simply a welding gun. The another patent I would like to mention today is about utilization of welding process for repairing purpose. Nowadays we are, I mean, discussing a lot about something called as restoration. You might have seen in other lectures as well, and repairing of the objects by welding process or by additive manufacturing process to recreate or restore the features those are lost due to the during the functionality, or I mean in the operational conditions. One such example is shown here. So you can see a brake drum, right? This brake drum got worn out because of there was a continuously acting some maybe mechanical system which was continuously due to the relative motion between the two surfaces. Of course, due to the friction, some of the material will get worn out from here, right? So to reclaim those worn out portion of the part, this machine was filed as a patent in 1930, which I have found, and the title of the machine patent was Machine for Reclaiming Worn Brake Drums. So if you read it carefully, you will find that it is nothing but utilizing a welding gun, that is MIG welding, to recreate the features onto the part, and that is nowadays we so-called call it as the repairing by WARM or restoration of the features by WARM. It was filed in way back in 1930. Then a patent I have filed, which was found, which was filed in 1957, was for the which was an apparatus for a vacuum deposition of the metal. It is nothing but your modern days electron beam gun. In electron beam also we deposit the material and the entire chamber is maintained in a vacuum. It was filed in 1957. Nowadays, very popular term is coming into picture, particularly for worm, is called as large scale worm, right? Large scale worm is not at all new. It was started long back in 1966, where this particular patent filed in 1966 discussed about the methods of and apparatus for constructing substantially circular cross section vessels by welding. So big vessels, you can imagine, can be just fabricated by utilizing the welding gun. So you can notice that here there's a motor. This motor is connected with the rotary axis. It keeps on rotating it with a constant RPM, and there is a welding gun, and this welding gun is attached on a Z axis. So there are two axes. One is the C axis, another is this Z axis, and whatever the position of this welding gun will be, it will keep on depositing the material, right? And it will keep on going up. So basically you can create the large storage tanks, cylindrical storage tanks, by utilizing this process. So this is a very good example of utilizing the wire arc additive manufacturing for large scale productions long back in 1966. Then in 1972 there is a patent which I have found. It utilizes multiple wires. Nowadays we talk about multiple wires to improve the deposition rate, or sometimes we utilizes these three different types of welding wires to make the on the spot alloy onto the melt pool. So high deposition rate, or the high deposition rate through the wire arc additive manufacturing, was long back explored by utilizing the multiple wires in 1972. Then I'll talk about some other wire-based processes, though our focus is wire arc additive manufacturing, but let me just talk about wire-based other additive manufacturing processes, metal, particularly for metals, is the laser-based system. It was a patent filed in 1979, where you can see that there is a laser which is creating a melt pool, and from the side you can feed the wire into it. And then you keep on depositing, and you can realize the features like you are seeing in this figure number 3. So laser wire metal additive manufacturing was long back filed as a patent in 1979, and they call it as method for fabricating articles by sequential layer deposition. Then in 1980, a method of coating thin film alloy on a substrate utilizing the induction heating was invented long back in 1980, where induction heating coil was used to melt the wire. You can see this rod here, it's a wire basically, and it is getting heated by the induction heating coils here. As the induction heating coil melts the wire but really cannot detach it, argon or some inert gas is supplied from the backside, which takes away these molten particles, and then they project it towards the substrate. As the projected on the substrate, you can build the part. Later on, of course, it took a lot of time, but in 1992, by Professor Dicken, PM Dicken, and the other co-authors you can see here of this paper, it was published in international conference, popularly known as solid freeform fabrication. It is known as, the paper is entitled as rapid prototyping using 3D welding. So here the welding process was used to build the layer, to deposit the material layer by layer on a substrate to realize the real objects. So this was basically later on where the welding was actually utilized to create the parts in 1992. Then after that, in 1997, a hybrid process came into picture, which is called as, which was filed as a patent, and you can find it as mold shape deposition manufacturing. So SDM, shape deposition manufacturing, is the popular name for the process, in which the manufacturing processes, not only additive, but the subtractive process, along with, as you can see here, the 30 number is the end milling cutting tool, are simultaneously used in such a way that you can build the objects. It was popularly known as the hybrid process that time. So the hybrid process is basically, according to me, was invented completely in 1997. So the idea why we were discussing about it is mainly to show you that worm is not at all new. It is not really a propriety of someone. Even the hybrid technologies, you can see that they were really filed as patent long back, and nowadays it's available for all of us to do the research and develop the technology further. So I'll just talk about the classification now. You have seen like many things, right, in the in different types of metal wire additive manufacturing processes. Particularly as today's focus is on the material which is only metal. So I'm writing here only metal, and it is because we are focusing on metal wires. Then how we are going to transfer the material on the substrate? Just continuously. Other process could be drop on demand or something that I have not written here. What type of machine tool is used? Why machine tool or the machine is utilized? It is basically utilized to give the relative motion between the substrate and the wire, right? So for that, different type of machine kinematics can be used, like serial kinematics, parallel kinematics, or hybrid kinematics. Then what kind of energy source is typically used? The energy sources like induction heating, arc heating, or energy beams such as laser or electron beam can be used to melt the metal wires. As I just came to know, it's like 4th day of the workshop. I am very sure now the participants are aware of what support mechanism is and why it is required in 3D printing. In a very similar fashion, in the case of when metal wires are used, again you require a support mechanism. But using another metal to support another metal, it is very difficult later on to remove the sacrificial material. So typically, there are two techniques popularly used till now in the metal wire-based additive manufacturing. First is acid bath, and the second is no support at all, where we use multi-axis kinematics. So what is acid bath? Acid bath is like, for example, you are depositing stainless steel, right? So you generate the support by utilizing the copper. Then later on, you put the whole thing, take the entire object which you created, the main material and the support material, and just dip into the HNO3 or like in acid. So what will happen in that case? The copper will get dissolved and remaining part will be your main material. So, but of course, now you can see that it only possible with a certain type of combinations, right? Not always with, I mean, with all the processes, it is possible. For all the wires, it's not really possible. So as support mechanism is not possible, then the next option available is deposit the material without any support and utilize the multi-axis kinematics. So what is multi-axis kinematics? So let me just draw and show this to you. Okay. Yeah. So for example, you can see I'm drawing this particular object. So assume that you want to deposit this, and there is an overhang right over here. So what I'll do to realize this overhanging feature, first I will build the part conventionally up to the desired location, up to here, for example. Then after that, I will tilt this table, right? For example, I'm using higher kinematics, multi-axis, not only 3, maybe 4 or 5 axes in the machine tool. In that case, this straight line will become like this, and the slant wall, which was earlier slant, will become vertical. So basically, you are always depositing vertically the part in such a way that no support is actually required, and that is possible by appropriately tilting or utilizing the multi-axis kinematics, right? So this is the classification. Now let me just tell one more thing over here. We shall discuss about in detail only MIG and TIG welding based processes. We'll try actually to cover the wire arc additive manufacturing, where arc is used to melt the metal wires. We shall not discuss about when the energy beam is used to melt the metal wires. Hence, we shall not discuss about the laser-based additive manufacturing or laser-based metal wire additive manufacturing or electron beam-based metal wire additive manufacturing. These two processes we shall not discuss, but we shall try to cover the wire arc additive manufacturing, where arc either by MIG, TIG, or plasma is used to create the melt pool, and in that melt pool we feed the wires. So this is now the first topic will be MIG worm, right? So what is MIG worm? In the case of MIG worm, all these options are possible. We can take the metal as the raw material. It can deposit material continuously. It will be having serial, parallel, hybrid kinematics for the machine side. Arc, as I mentioned, only MIG will be used. It is possible to use no support with without having any support. There is no option, I mean, and it could be the multi-axis kinematics as well. So what you are seeing on the right side of this slide is the typical setup for the MIG welding base or the MIG worm. Here you can see there is a deposition unit, which is a MIG welding gun. This MIG welding gun is nothing but consisted of a wire feeder, which continuously feed the wire, and there is a circuit completed between the wire and the substrate. That again we shall discuss about what kind of polarity is used, what is negative, what is positive. It depends, and that changes your results as well a lot. But assume that there is a wire over here, and as this wire feeds towards the substrate, due to the gap between the electrode and the cathode and anode, a arc is initiated, and further we supply some inert gas through this black color line, and that arc also further helps in sustaining this arc, and this arc creates a melt pool in the substrate, and continuously this wire keeps on melting and we keeps on feeding the wire. So the electrode here is consumable. Now what we need is nothing but the relative motion between the deposited wire or the melt pool and the substrate. So to give that relative motion, we typically can use a CNC controller. CNC is nothing but the computer numerical control. It can be a robotic arm or a CNC machine or a 3-axis robot, in other words, in a more generic word. But this control has to be through the computer. We cannot do that manually. Otherwise, it will be very difficult to deposit the desired shapes. Right. So let us now the consumable electron in the form of the wire reel, which is continuously fed through the rollers, and in such case the welding wires get consumable, and they are not only just creating the arc but depositing or adding the material also onto the substrate. So what kind of polarities I can use? I think it maybe many of you are already aware of it, but just let me quickly tell about it because it's required when I'll discuss about a very important welding process for WARM and popularly called as CMT, cold metal transfer. So what really this polarity do basically? There are two types of polarity we can use in the case of the welding power source. It could be AC welding or the AC machines, alternating current machines, or they could be the direct current machines. What happened in the case of direct current welding or the direct current arc welding or the DC arc welding? It is generally preferred, particularly in MIG welding, it is preferred that we generate 70% of heat near the anode, right? And anode we usually make the wire, right? And why 70, like more heat is generated typically towards the anode? Because the electron travels from cathode to anode, right? And when they strike, they generates the energy. So that is why because from negative to positive electron travels, right? That is why the more energy is generated on the positive side, right? We need to remember that. So now let us consider two types of polarity. One is straight polarity, or also popularly called as direct current electrode negative, right? So in such case, what will happen? More heat will be generated onto the substrate because my electrode, the wire, is negative, right? So more heat will be generated on the positive side. So more heat will be generated on the positive side, and that is why we will get more penetration. Correct? Other polarity could be reverse polarity, where the electrode is positive and my substrate or the workpiece is negative. In such case, material will get deposited more, so more deposition will happen here, but the bead, the penetration of the substrate won't be much as compared to the straight polarity. So as I already mentioned, in the first case 70% heat was generated on the substrate. In the second case 70% heat was generated on electrode. If you use AC welding, 50% are generated on both the wire as well as on the substrate. In such case, you get somewhere moderate penetration of the substrate as compared to the DC straight or reverse polarity. It is somewhere in between. So let me just tell you the different type of metal transfer in such cases and what is actually preferred in the case of additive manufacturing. So in the MIG welding based process or MIG welding process, the filler metal is transferred from the electrode to the substrate depending on the current and voltage which we use and which we give to the electrode. The metal transfer is done in the following three ways. Those are short circuit or dip transfer, or the globular transfer, or spray transfer, pulse transfer, or rotating spray transfer, right? You know that these types of transfer are governed by the two forces, as you are seeing here. These forces are corresponding to the Lorentz force and the direction of the current in which it is flowing, and of course the gravity, the gravitational force, which is acting the downward direction, in the downward direction. So the range of current is typically low for the short circuit transfer, while it is typically high for the spray transfer. Relatively, the amount of current which we supply is higher for the globular transfer, and it is somewhere in between for the pulse spray. Of course, for rotating spray, it's further increased, and it is the highest for the rotating spray. So the above are found to occur with varying rate of current, right? You can see that. So it is very important to see what kind of metal transfer is really important for additive manufacturing, and that is why we are just revisiting our whole thing again, right? We want to see exactly what kind of metal transfer will be suitable for VARM. So the above found to occur with varying rate of current, the lowest rate giving the short circuit transfer, right? This is giving the lowest current. So if you use the lowest current, what will happen? Let me just try to explain to you. If there is a wire and there is a substrate and current is not very high, so the substrate will, the wire will just strike the substrate. As it strikes the substrate, the circuit is completed, and as a result, you know that the voltage become zero, and there is a characteristic on the power source side. It increases the current and breaks the wire, right? As soon as the wire breaks, the current comes to its initial position, and again the process itself repeats. So it basically short circuit the entire loop, and it is typically handled on a low current. Let me show you some videos for each of these process, and then you can realize which process will be suitable for wire arc additive manufacturing, right? The first one is short circuit metal transfer. You can see that there's a wire coming and it is creating a droplet. Further, the wire is dipping into the melt pool. As soon as it dips into the melt pool, it short circuit, right? Because the circuit gets completed. As a result, the current increases and the necking start, and basically it melts away the wire at the desired location, right? While the second case you can see is for the globular metal transfer. So what happened in the case of globular metal transfer? There's a wire, right? And you supply a right amount of current, and as the current is sufficiently high, it will melt the wire here itself. It will not wait till the short circuit will happen and then the current will increase. In that case, what will happen? The droplets will be formed, the droplets of the metal will form, and they will fall into the melt pool. The second is spray metal transfer. In the case of spray metal transfer, the droplets are tiny, right? And it is predominant with the argon as a shielding gas, right? It depends on what type of shielding gas, because that increases the flowability further of your metal which you are using. And the droplets are transferred like a spray into the melt pool. The most preferable is none of these above. The best one is the pulse metal transfer typically. Though the DC welding short circuit globular can also work, but the pulse is preferred. Why so? Because the average energy used in the case of pulse metal transfer is quite low. You can see what exactly is happening here. The arc is illuminating and then again reducing its illumination, right? It is happening not because the wire is striking into the melt pool and completing the short circuit. No, it is not short circuiting. Instead, what is happening? There are two types of current here. One is the background current, another is the main current. The background current just maintain this arc, which was just make sure the arc is sustained, while the main current makes sure that the wire gets melted and detach a droplet which can travel towards the melt pool. That is nothing but the pulse metal transfer. So in this case, as we are transferring the we are giving the right amount of current, particularly for the right operation, the average power is quite low, and average, as the power is low, of course the average heat input will be low, and you can really deposit the material with least dilution. And if the penetration or dilution in the substrate will be less, it is very much suitable for additive manufacturing to sustain the features which we are depositing. Further, in the case of spray metal transfer, if you further increase the current, it may happen that the wire will start melting, and instead of transferring into the form of droplets, it will be continuous metal transfer, and it will make a you can see that this type of motion due to the particle, the metal carrying the current moving into the electromagnetic field, and definitely due to the forces acting onto it, it just deposited like in a circular form. But none of these are suitable for additive manufacturing or wire based additive manufacturing process. But then later on, there is a process came into picture called CMT. Still, I have mentioned just now that there is a current required, right, to detach the wire from the short circuiting. But what if we mechanically detach the wire, or we pull the wire back in such a way that it can detach a droplet onto the substrate? So the cold metal transfer MIG welding is one of the most preferable MIG welding process due to low heat input characteristics, and primary characteristic feature of a CMT MIG welding process is alternating thermal pool. So the melt pool is hot, right, when the arc is initiated, and it is cold when arc is extinguished. And how we detach the wire? We do not detach the wire by increasing the current. It is instead detached by, you can see in the third number step, by pulling the wire back. So the steps involved in the CMT cold metal transfers are written here. So initially, when arc is initiated, the filler wire moves towards the substrate, right? Towards the substrate. As the current is less in the beginning, assume that it is some amount I1 and it is very low current. In that case, the wire will keep on moving towards the substrate because the current is not sufficient enough to melt it before reaching the substrate. As the current is less, like I mentioned, the wire will dip into the substrate, like it is shown here in second number. Right now, what we were doing earlier in the case of short circuit metal transfer, right? You just have a look at it. It was touching, and we were increasing the current through the power source. But instead of doing that, what we can do, we can pull the wire back. If we pull the wire back, the droplet will remain with the substrate, and wire itself will move back. You know that because the contact area is large here, and the wire alone, without taking the droplet along with it, will move back. As soon as the wire will move back, the desired gap will be obtained, and as the desired gap will obtain, the process will again repeat itself, right? So these four processes, 1, 2, 3, will keep on repeating. There is a mechanical motion of the wire in the case of CMT cold metal transfer, and it is very much suitable process for additive manufacturing. You can see the video that can explain you how it really works. Yeah, so here you can see the wire dipped into the melt pool, and it is just leaving the wire, leaving the droplet into the melt pool, not because of the high current, right? It is leaving because the main wire is moving back, right? It is moving back, and when it is moving back, it is leaving the droplet onto the melt pool. This is cold metal transfer. In such a case, not very high energy is really required. Very less energy, very less amount of energy is used to melt the wire, and you can have a very controlled deposition in that case. So this is about the cold metal transfer. Now I shall discuss about the process cycle of the same. So I just want to know, I mean, if there is any question, you can raise the hand, or you can, I think, type in chat box. I can see the chat box over here. Yeah, or you can unmute also. I don't know if that is possible. I'll be very happy that if you unmute and we can discuss also. Otherwise, I'll just keep on talking for 1.5 hours. May not make much sense. So if you have any questions, please feel free. You can unmute and we can discuss. I'm just taking 2-minute break. Just 2 minutes. I mean, I'm here only, but if you have any doubt, let me know.
Participants can unmute themselves and they can ask their questions directly to the expert.
Yeah. Thank you, Dr. Kailash. Actually, they can unmute, right? They have that.
Yes, they can unmute. Alternately, participants can write in chat box.
Yeah, okay. I think I'll continue. It just to let you know, if you have any doubt, feel free to ask in between itself. Okay. So like other additive manufacturing processes, here as well, we shall start with the CAD model, and then we generate, sometimes it's STL file, sometimes we do not generate if you are using an appropriate CAD package. But the other process is very much same. You generate the G code, transfer it to the machine, it will deposit it according to your G code, and then if required, later on you do the finish milling operation of your machine, and then it goes for the final component. So the process cycle is very much same what we have already seen, you might have already seen for other 3D printing processes. So but instead I will talk more about the affecting process parameters, what really affect the process parameters for a warm system. So whenever, for example, you are going to deal with a new material for warm, we usually conduct three types of experiments. The first is called as the single bead experiment. The second is called as multi-bead experiment, and third is called as multi-layer experiment. And that is how you build your object as well. The influencing process parameters in the case of MIG warm are written here. Those are like power related process parameters such as arc voltage, starting, main, or reducing and the final current of the welding, filler wire, what type of wire it is, right? Like composition of the wire, it's aluminum wire, steel wire, or what kind of alloy it is, what kind of coating is there on the wire, what is the diameter of the wire, what is the feed rate of the wire. Usually in the case of MIG welding, this feed rate is in synergy with the current. If you increase the current, wire feed rate will also increase. The gas, what kind of gas we are using, the proportion of the gas, the pressure of the gas, the flow rate of the gas, the deposition, I mean, what kind of layer thickness you are using, what is the width of this bead which you are depositing, what is the height of this bead. The torch related parameters are like what is the distance between the nozzle and the build plate while depositing the material, the distance between electrode contact tip and the base plate, and the torch speed, but what speed you are moving your torch onto the substrate. And then in the end, the path. The paths are like what kind of area filling strategies you are using, and what is the distance between two consecutive passes. For example, there is the one pass, how far is going to be the next pass. So all these are the process parameters influencing the wire arc additive manufacturing process, right? So let us first discuss about the single bead experiment, right? So a single bead experiment usually conducted to obtain the shape of the or the profile of the bead which you are depositing. So assume that if the deposited bead's profile is parabolic, right, as you are seeing here, and it is represented by a curve y equals to a plus cx square, right? There will be definitely some penetration as well into the substrate. In such case, I can easily find out the value of the constant a and c, because if I know the height and width of the bead, right? So if I put the boundary conditions, like if x is equals to 0, that means in that case my value of y, at x equals to 0, the value of y is going to be h, hence a will be equals to h. Similarly, if I say at x equals to at y equals to 0, it means at this position where the y is 0, right, you can find out easily the value of x as well in that case, right? So these two boundary conditions, if you put, your final equation of the parabola which is representing our bead can be obtained as y equals to h bracket 1 minus 2h by w square. So the point why I'm doing it at all is because I want to obtain the distance between the two consecutive beads. Like for example, if this is the bead, what will be the distance between the next bead? Just let me select the pen. Yeah, if this is the first bead, what should be the distance between the next bead and the first bead? So this is important. If first understand what is the profile of the bead. So that we assume to be as y equals to a plus c x square. As I already mentioned, if you know the boundary conditions, the boundary conditions are like at x equals to 0, at x is 0, at this at which position, sorry, at this location, right, x is 0, and at x is 0 at this location, the value of y is h, right? Similarly, we can put y equals to 0 and y is 0, we can see at this location, right? Wait a minute, this is something wrong. Yeah, at this location, and here the value of x is w by 2, right? So we can put it w by 2 and we can find out the value of c as well. So if we find out the value of a and c in terms of height and width of the bead, then the equation of the parabola can be written like this. Okay, there is a question from Shweta Ansari. No, it is not necessary that your bead will be always parabolic. No, it's an assumption. But why I'm doing it, you will appreciate it immediately. Even you can consider it circular as well. That will also, but the method of obtaining the distance between the two consecutive beads will remain same. That I can assure you. Okay. You can even fit a non-linear parabola also in that. I mean non-linear polynomial into that. No need to have like only the parabolic or this whatever the conic shapes. It can be any polynomial also. So basically, once you got the shape of the bead in terms of h and w, the height and width of the bead, now we can easily find out the one of the parameter only in terms of h. Like for example, if h is written here and width both are written, it may be difficult for me to measure both of these parameters. I can easily measure the height. So let me try to replace this w in terms of only height, only h, because if I do that, it will be very helpful for me. So what I can do, I can utilize the mass balance equation, right? I can just make sure that the mass is consistent. So if there is a welding gun, right, there is a wire coming from it, and this wire is coming with some speed. Assume that this speed of wire is given as VW. So what will be the mass flow rate or the volume flow rate for this? We know the area of the wire, right? And if I multiply it with the velocity, that will give me nothing but the volume flow rate, right? And that will be nothing but pi d square VW by 4. And also it is depositing the bead on the bottom. We have seen that. So bead also should be deposited with the same rate by which it is coming, the material. We know the cross section of the bead. We assume it to be a parabola. Hence the area will be 2 by 3 HW. And if I'm moving this entire torch with a velocity Vt, right? If I multiply this Vt and the deposited cross section, I can get the rate by which I am depositing the material. So input and output should be equal, and that is why this equation is coming into picture. Finally, further if I simplify it, I will have W equals to 3 pi VWD square by 8H VT. So I can have now the entire formula in terms of only one unknown parameter H. So what you can do, you can just deposit the bead and measure the height H of the bead, and then you can find out anywhere on the bead the height of it, right? You have the parabola. Now you know the maximum height, and then you can find out the height at any location. This formula can help you in that. Other parameters are already known to me. H is already measured. Velocity of the torch is already known, right? Wire feed is also known. Why wire feed is known? Because we know the current. And whenever you buy a welding machine, there is a synergy between the current and the velocity of the wire, which is by which the wire is getting deposited, wire is getting feed. So if we have this synergy between the current and the VW, then there is no issue, and you can you can easily find out the value of VW. Then again, the diameter of wire is also known to us. So you can easily find out. Again, I have mentioned, I can say that this is a very crude assumption that we are assuming the parabola for the bead shape. It can be anything. It can be some other polynomial also to represent the shape of the bead. Need not to be parabola always. That can be further explored. But this is the most simplified assumption, and it really works. Let me tell you, it really works. So, like I already mentioned, for each welding machine, you will have this type of curve called as the current versus wire speed, and you can easily obtain this even by experiments also. So once you have that, for a particular current, you can find out what is the speed of the wire, and current is my input on the machine. So now the interesting part is, you know the equation of this, right? Completely, you know the height as well. So what I want to make sure that I deposit one bead and the second bead at a distance apart P in such a way that the deposited bead should be flat. I mean, the two bead should result in the flat layer. What are the possibilities? Let me try to explain to you. If they are perfectly at the right amount of distance, perfectly good amount of distance, then what you will have the overlap area flat, because the material which is getting overlapped here will bulge out like this on the top. So if it is a perfect overlap, then you will have a flat surface. If the overlap is high, I mean to say the distance between the two beads is relatively high, then in that case you will have a concavity here. And if it is low, for example, these two deposited beads are very close together, then definitely you will have a converse shape here. Extra material will be deposited. So what do you want? We always want this case, right? So just use simple mathematics. What we want, we deposited two parabola, we just draw two parabolas. What we are saying, that we need a straight line. So I draw a straight line on the top surface. Hence, in other words, I'm saying that the area which I'm hatching right now, right, this one represented by FEG, this area should be equals to the area GHLJ, right, this area. If they both are equal, then definitely you will get a flat surface. So further I can simplify it. I can simplify it like this, like only area H. I hope my pointer is visible. Let me just change it. Yeah, the point H L G, this area, right? Only this area should be equals to the area FIG. So once I can say that these two areas are equal, then no issues will be there at all. I can simply do my double integration, right? You know that how to find out the area under curves. So I'm going to integrate from this curve to this straight line, and then in the bottom case I can do integration from this line to this parabola. So if I can do that, I can say that the area, if these two areas are equal, then you will have a flat surface. So let us do the same thing. I just simply doing the integration, and we have already derived this equation, if you remember, y equals to h1 minus 2x by w square, right? Just few slides back. If the shape of the object is shape of this deposited bead is considered to be parabola. Hence, if I just solve it, you will find that the value of P is coming to be 2/3 of the width of the bead. So if the width of the bead is W, then the optimal distance between the two consecutive beads should be 2/3 of W. And that is true when I am assuming again the shape of the bead parabola. Now if somebody just asks me, what if the shape is something else? Then of course you will have another equation between the y and x. And of course the boundary conditions will write here h and w. So you can consider anything, put the boundary conditions, get the equation, but again you have to again further put back into this equation to find out the optimal overlap. So whatever the shape is, the same procedure can be used to obtain the optimal distance between the two consecutive beads. So that is how you obtain the deposited beads with the optimal overlap. So this is an optimal overlap in the case of MIG welding. Now in a similar fashion, it is not always that the scenario is not same, that you keep on depositing the material on a flat substrate, and when you deposit on a curved substrate or or already deposited layer. So such study was done by Professor Surya a few years back from IIT Hyderabad. So they have identified, if you deposit the bead on a flat surface, the parameters you obtain like height and width are different. But if you deposit on a curved bead, like you are seeing here, then the parameters corresponding to the height and width are going to be different completely. So what can we do? We can just it's a very simple mathematics. It's already been explained in one of my lecture. I will share the link in the end of this today's lecture, and you can go through it, and you will find that it established a very simple formula between the nth layer deposited on a curved bead in such a way that you obtain the height h. Remember that the height h you are obtaining on the flat substrate will not be the same height of the deposited bead when it is deposited on a curved bead. So you need to be a bit careful on that side, right? Let us talk about now some mechanical properties for the material deposited by Mig Worm. So for example, when you deposit material, its hardness keeps on changing from bottom to top. Usually the hardness is quite high on the top layers because the microstructures here are quite fine, because they do not go through the several thermal cycles like the substrate goes through, right? The substrate goes through many thermal cycles, right? It got heat up, then cool down, heat up and cool down, and due to that, what happened? The microstructures become porous and hence hardness is also reduces. The tensile strength of the parts, usually it's less in the direction of the deposition. This is because of the less dilution, and that is sometimes preferable. But if you do more dilution, you can obtain close to the strength of the material which is in the XY direction, but typically it is low only in the direction of the build or the build direction. As you can see, for the mild steel, the UTM is represented here. It is around 20% weaker in the yield strength in the direction of Z, I mean in the build direction, as compared to the strength obtained in the XY direction. Those are represented here in the blue and the red bars. The ultimate standard strength, like I mentioned in the Z direction, can be further improved if you improve the dilution. For that, you know that you need to increase more heat input to the substrate, and that can be done easily by improving the current. So if you keep on improving the current, definitely the dilution will be increased. As the dilution will increase, your strength will increase. But you have to stop at a certain point, because if you increase the dilution too much, it may happen that your overhanging features may get distorted because of the high heat input, and you may not be able to really sustain the deposited weld bead onto the pre-build or the substrate layers. Let's talk about now some defects in worm. The very important defect popularly nowadays discussed by many researchers is the residual stress distortion. The residual stresses are usually nothing but the remaining stresses into the part after removal of the all external forces. Like you are clamping the object, after remove it, it will just get warped. I mean, it will release some stresses, but those stresses, those are get remain into the part, are called as residual stresses. So the residual stresses in the part may lead to distortion if you when we remove the load, or it also adversely affect the fatigue life of the part if those stresses are remaining there. If the residual stresses in the part is more than the UTS, the tensile strength, then it will lead to it may lead to the cracks. And if it is more than yield strength but less than the UTS, then it will lead to warping or the distortion, right? So it is almost impossible like to eliminate these residual stresses from the parts produced by worm. However, an appropriate tool path strategy can significantly reduce it further. So to understand the generation of the residual stress in the worm, two models are usually used. One is called as the thermal gradient model, another is called as cool down phase model. So let me try to explain to you the cool down phase model, how it works. When there is an arc, right, as you see here, it creates a melt pool. So what is melt pool? Basically, when the solid metal is getting converted to liquid material, it starts expanding, and as it expands, it pushes the walls. Those are solid here, and as a result, as it is pushing, the solid will resist this push, and it will be having the compressive residual stresses into the material or into the substrate. As you can see here, into the center part, which is liquid, no stress will be there. But if you go away from the melt pool, the stresses will keep on increasing on the negative side, meaning to say the compressive stresses are increasing and they become constant further into the substrate away from the melt pool. Now what happened when the arc passes away from a location, the melt pool now starts getting shrinkage, as you can see here. And it is typically in most of the metals, not all I'm saying, but in most of the metals, the melt pool start getting shrink because it is getting solidified, and as it is getting solidified, its size is going to reduce. So what will happen? The solid portion of the base metal will try or will resist this motion of the solidification, right, or this shrinkage. As a result, this shrinkage will pull this base metal, as as a result, it will lead to the tensile nature of the residual stress. So earlier the stresses were compressive, right? So now they will keep on adding, and they will move towards the positive residual stress, and finally they will end up having some amount of tensile nature of the residual stress into the part. So this is how typically a residual stress cycle for the mild steel works, but it may change and it may further depend on the heating and cooling, solidification, shrinkage, all these behaviors of the material, and different type of materials may lead to different type of residual stresses. Like I already mentioned, if the residual stresses are higher than the UTS, it may end up having the crack into the object, and if it is higher than yield strength but less than the UTS, then it will lead to some warpage or permanent distortion into the part. If it is less than yield strength, no issues, it will come back, because you know that, right? There will not be any permanent distortion. Yeah, any doubts? Okay. Few more defects I'll talk about are like the porosity. Porosity is another very common defect observed in the parts produced by VARM, very common. So the porosity in VARM will lead to component with low mechanical and the fatigue life. The porosities are usually classified in VARM in two categories. One is called as raw material induced property, raw material induced porosity, and another is process induced porosity. So what is raw material induced porosity? It is due to the contamination. You are depositing some material and it may get contaminated, right? And the process induced porosities are due to the poor path planning and unstable process, like your arc is getting distinguished, you are not using appropriate process parameters like current or whatever the parameters you are using, you're not using appropriate tool path. Those are some issues related to the path planning. But these porosities are typically can be controlled. You can see one of the impeller I built long back in 2014, or I think in 13. The porosities are quite visible, and I know the reason as well. So because that time we were more focused on obtaining the shape, but later on we realized that we need to make a very perfect impeller, so we rectify the issues. So how we rectify these porosity related issues? What if you are getting such porosities, what could be the possible reason? So for example, an AC MIG welding process or CMT is preferred, particularly for aluminum, to avoid the porosity, because when you deposit aluminum, its flowability is quite high. I mean, the liquid material is quite flowable. As a result, the gases, those are the inert gases, get trapped into it and they come out and they create the porosities behind. So it is good that we do not increase the temperature much for aluminum or such low melting point temperature metals, and we use the process like AC MIG welding or the CMT MIG welding. Other possibility could be we use high quality shield gas and non-organic piping, because wherever the organic piping or something is there in the welding, and any contamination, organic contamination is there, the hydrocarbons break, you know that it creates some gases and they escape in the form of leaving the porosity in the back. So it is very important that you clean the wires and substrate appropriately. We also use high quality of feedstock, because that also happens many times. We use the optimal bead shape. Like for example, you look at this one. It is very important, right? So for example, in this case, there is a lack of fusion, meaning to say the deposited material is not having a very good contact angle. Its contact angle is in this direction. Assume that I am measuring the contact angle from the substrate from I mean in the anti-clockwise direction from here to here, and it is less than 90 degree. It is not preferable, because if you deposit now the next bead next to it, what will happen? The material may not be able to flow into the corner of this, because of the surface tension of the material, right? It cannot really flow everywhere. So what will be there? It will be having a porosity. Simple. But if you are having a concave surface, I mean a contact angle measured more than 90 degree, then it is possible that such issues may not arise. Okay, it will be very, very important parameter. The first parameter you should look into. Do not prefer to have a bead shape like this, because they are not good when you deposit multiple beads one over alongside. The process monitoring is important, and of course there are sometimes no way of eliminating the porosities, so you need to go with some in situ and post processing to eliminate this. There was a, I think, question. Let me just have a look at it. So yeah, is it possible to do welding on sheet metal component, because most of the time porosity could be seen in sheet metals? Uh, okay, I think metal, any metal is there. If there is a porosity, I mean, I didn't get the sheet metals. Are you saying the sheet metal? I understood that it's like a metal with some less thickness, right? In that case, yes, you will not be having a sufficient melt pool, and in that case, preferably you should go with cold metal transfer type of process. But if sheet metals are having already porosities, uh, I'm not sure how you can eliminate. So what we can do, you can unmute and ask. I think I'm not able to understand your question completely.
Sir, good morning, sir. Sir,
Yeah.
Prashant here. Sir, actually, sir, as we can see that in some of the components like single cylinder engine, we use a sheet metal protective sleeves. So over there, whenever we just made that component, we uses generally brazing process over there, just because welding is not possible on sheet metal just because of their thickness. But sir, whenever we just joins them now, there we can just face the problem of porosity.
Okay.
So sir,
It may not be called as porosity. So
yes,
I got your point. But what you are saying, that if you are joining thin sheets, right? Thin, I mean not thick, right? Am I right?
yes, sir. Yes,
Yes.
sir.
What happened, usually you get more penetration, and due to that more penetration, there is a metal which is not getting joined, and it leaves a gap in between, right? So let us call it as gap. It's not really porosity. So those gaps are coming because you are giving a lot of heat. So you want to reduce the heat input, but you still want to deposit the material, right? So that is why
Yes, sir.
in that case, you go preferably with cold metal transfer or a proper path planning. So if it is an industrial problem, Mr. Prashant, I mean, then you let me know. We recently developed a tool path, okay, for welding, in which you can join really very thin sheets. It's not always only the process. It's based on how you are depositing, right? What is the method of I mean depositing the material in, that also optimize the parameters drastically, and I can assure you that, I mean, we can really deposit the material on very thin sheets, but by appropriate toolpath planning. So if you want, Mr. Prashant, we can discuss further after the lecture. I'll share my email ID and then we can discuss
Yes,
about.
sir. Thank you, sir.
Yeah. Okay. Yeah. Other, the last defect for MIG worm process is high temperature and material characteristics are major reason for the crack. The defects are crack and deformation or the delamination. So the reason for crack, there are two reasons possibly for crack. One is the solidification crack, another is grain boundary crack. The solidification crack usually observed due to the obstruction of solidified grain flow or high strain in the melt pool, right? And the grain boundary crack usually occur due to the difference between the boundary morphology and the potential precipitation formation in the uh, and the grain boundaries, and they do not able to, I mean, show the appropriate morphology, and the grain boundary itself shows the crack. The delamination between the adjacent layer basically comes by the two reasons. The first could be the lack of fusion, because you are not giving enough energy, right? And another is mainly the Resolute stress again. And in that case, what happened? You are depositing two layers, they just delaminate like this, right? They just get apart. So what is the solution for delamination? Like, because I said it's lack of fusion, instead, even if you are increasing the current, that's not helping you much. So in that case, you need to sometimes do the preheating of the substrate, so that you can now deposit the material, and there's a possibility, good possibility, that good adhesion may take place. So this is the material versus different types of defect we observe. Like the red color curve is corresponding to the titanium. You can see that the titanium is having lot of issues related to the defect corresponding to the oxidations, because it's a very reactive material, you know that, while the issues related to delaminations are not really much. Other materials, let me take this, let me just consider a material, aluminum. Aluminum must be having the very difficulty, the most important property defect observed in aluminum is the porosity. So you can see that, yes, the aluminum is having the defect very much observed, particularly related to the porosities and deformation later on due to the residual stresses. So they both are at the same level, but porosity is quite high. But the party deposit by aluminum usually are very good surface finish. They're not really having very bad surface roughness, right? So this type of things you can observe from here corresponding to the material versus defects. So let me just see how much time do I have. Okay, I'll take 10 more minutes. So I'll quickly cover the TIG worm again, TIG worm process. So till now we have seen the MIG welding process. Now let us discuss a bit about the TIG welding process or TIG welding based wire arc additive manufacturing. So in the case of tungsten inert gas welding or gas tungsten arc welding, the tungsten is not consumable, right? It is a non-consumable electrode which just generates the arc, and then that arc creates a melt pool. Now please note that this tungsten is not going to get melted. So this is a non-consumable electrode, and then you have to feed the wire from side into the melt pool created by the arc. Though these processes are the TIG based processes are relatively more precise than the MIG based process, because you have now two separate controls. You can control the wire feed rate separately. You can control the arc, the arc or the current, and the correspondingly the energy separately. They are not like merged. In the previous case, you might have seen the wire itself was generating the arc, and that it was getting fitted. It was not really a, very optimal thing to do, right? But here you have two different control, one over the welding wire and one over the arc generated. That is the main difference. But it leads to also, due to this asynchronization, the deposition rate in the case of TIG welding or TIG worm is low. It's not really beyond like 30 gram per minute. Yeah, by some methods we can achieve, but not really always. While in the case of MIG welding, we can go up to very high deposition rate, up to 60-70 gram per minute also. Very much similar, the process here for TIG welding. Here also we use AC, DC, and AC in different polarities. Like this is an example of DC welding current, where you can see that two types of currents are used. As you can see, it's flashing, right? It is maintaining the arc, and then the another pulse is corresponding to melting the wire, right? So it is in pulses. And you know that the purpose of having pulse, because the average energy is less, and as the average energy is low, you can give low heat input to the substrate and hence less dilution. It is good for additive manufacturing to avoid many of the defects. Another variant of TIG welding is plasma. In the case of plasma, what happened? The tungsten is inside this nozzle, and this nozzle is having a shield gas, that is argon, the inert gas basically coming through, and that the inert gas has now two purposes. One, to of course the product the melt pool, which is also called as shield gas or the shield part of this inert gas. Another is the inert gas goes into the close to the arc, the tungsten over here inside this nozzle, and it gets ionized and comes out in the form of plasma. So there is no protrusion of the electrode anymore. The plasma gas now basically gives us sufficient energy to melt the wire as well as the substrate appropriately. It's a variant of MIG welding only. There's no much difference. And this is how typically a TIG welding based process looks like. You can see there is a tungsten electrode, it's creating the arc, and that arc is creating the melt pool, and then that melt pool we are feeding the wire. Correct? Very similar fashion, you have a system in which we are feeding from the side, from the bottom side. There is a electrodes creating the arc, and then that arc is creating the melt pool, and in that melt pool we are feeding the wire. Robot based system is shown here, where a plasma is used. You can see that this is the plasma, even without having a complete circuit with this substrate. It is having a pilot plasma with it. It's not the real plasma, it's pilot plasma just to initiate the further plasma, and the wire is coming from the side here. The process parameters are very much same. The only difference, like I mentioned, is that now you have a separate control with on the current and the wire feed. You remember that in the last case the wire feed was synchronized with the current. Here they both are same. Sorry, they both are separated. You have separate control on wire feed, you have separate control on current, which is generating the R. Yeah, we need to, I mean, if you are going to work on the system, you need to consider very important phenomena of the metal transfer. Like in the case of MIG welding, it was a bit complicated. Here it is not that complicated, but what the three things you need to consider: if your wire feed is very low, right, as you can see in this diagram, the wire feed is very low. So what is happening? This arc is there and the wire is getting melted before even reaching the melt pool, because the wire feed rate was very low. So it has absorbed enough energy and getting melted, and hence transferring the material in dip form, like drip transfer. It is also called a droplet transfer, right? It may also happen that the wire feed is very high, as you are seeing in this diagram. In that case, wire won't be able to catch up enough energy from the arc, and it will get melted by the energy available in the melt pool, right? And when it will happen, the solid portion of the wire will hit the melt pool, and due to that you will have some issues related to the deposition of the wire. What is the best one is the and this particular method is called as wire plunging. The best is the bridge transfer. In the case of bridge transfer, we have a wire and that wire gets melted and it creates the droplet. Now that droplet touches the melt pool and hence created a bridge between the melt pool and the wire, right? This is called as bridge transfer. So what is important now? You have to set your current, right, that is the energy corresponding to the arc, and the wire feed rate in such a way that you get obtain the bridge transfer. Otherwise you won't be able to get the absolutely good be deposited on the substrate. Also it is important that where the wire is getting melted, whether it is getting melted at the center or it is getting melted just before, because it may happen if the welding is not getting melted at the wire is not getting melted at the center, your bead will get offsetted. It will not be really at the center while depositing. So you can do that by some simple mathematics, but let me just skip it as we may not have much time, but I shall discuss about another phenomena which is called as omnidirectionality. So what happened in the case of MIG welding? There is an issue. As you can see in this video, the wire is getting fed from the side and you are moving on a circle. So it is now right now front feeding. You are feeding wire from the front, and then again you are feeding the wire from the side, and then you are feeding the wire from the back, and then again you are feeding the wire from the side. So different type of feeding mechanisms occur while you depositing the material on a non-linear trajectory in the case of MIG welding, and hence as a result your bead shape may not remain constant. So you need to have a solution for this. So what are the possible solutions? I'm just going to show you quickly. Either you use wire from the center as you are seeing here, but in that case your electrode, the tungsten, should be hollow, right? And it should create a hollow arc which should get converged, of course, at the bottom, and the wire should come from the center. But you'll be surprised to know a very old patent has been found on this method. People have already done it, and it is good now. If the wire is getting melted at the center, now you can move in any direction and you can deposit the material, and process will become nice and it will not create any issue. Another is you take care of the machine tool. Like for example, here I'm rotating the substrate in such a way that always front feeding is maintained, right? As you can see here, as always the front feeding is maintained. You appropriately move your gun and the process will remain perfect. Yeah, you are saying something, sir. Yeah, someone was saying something. Okay. Fine. So another possibility could be that your wire feeder can rotate around the melt pool created by the tungsten, right? Dr. Kailash, I just want to know, do I have time or I'm
We have time till 11:30, sir.
we have time. I mean, for me it is
We
yeah,
have 15 more minutes.
okay. Okay, because I saw some chat people are saying thank you, so I thought that I'm stretching.
No.
Fine. It's okay. So I mean, yeah, you can deposit the material by appropriately rotating the wire around the melt pool. So the let me make it in summary. If you're using TIG welding, you can't just really retrofit it on a machine like CNC machine or maybe on a robot and then directly use it. You have to be, if you really want to build something really useful, you need to be more careful in the case of TIG, because here you want to make sure whether your wire is appropriately rotating around the melt pool or not, right? In what condition it is happening otherwise. Otherwise, you have to make sure some auxiliary arrangements with the system in such a way that then only it will be possible to deposit the material appropriately. Yeah. So the manufacturing systems are almost same like we discussed for MIG welding. These are some examples from the WAM 3D Limited. They have deposited big titanium tank out of the by utilizing the plasma and feeding the wire from the side like this. And as it's axisymmetric object, it may not have any I mean much issues related to the deposition of the related to the omnidirectionality, which we just briefly explained. So let us now discuss quickly about some popular single station hybrid systems. All right. So this is the WAM system in IIT Bombay, where you can see that a single station, meaning to say a CNC machine is used on which multiple guns are mounted. They can deposit the material. You can even mount multiple guns on the CNC machine, and such systems are popularly called as single station CNC based system. There is a system in USA, and the courtesy is written here for the Professor Christopher, and you can see in this system the welding gun is not really mounted on the side, right? It is very innovatively mounted along with the tool post itself, and you can see that it's a single station system. Then after that, the 5-axis system, the commercial 5-axis system I'm going to show you here is from Guwahati,
Etablierte Methoden.
where there is a big 5-axis machine is used, where on the center there's a welding gun, and then it is depositing the material onto the parts created, where the part can also be tilted by utilizing a rotary table, right? So this is the name of the company done here, Guwahati. Then this is the 5-axis system which I used during my PhD starting in 2013. So here I'm depositing this impeller in long back in 2013, even before the machine launch of Guwahati in 2018. So here you can see that the impeller is not only built by layer convention of horizontal layer manner. It is deposited in conformal layers. Like first I'm depositing the center part, right? And then on the center part, these red color blades will be deposited, and the growth of the part will be not like in a horizontal layers. It will be conformal, right, to the deposit, to the base, to the hub of the impeller. And then this is how you can build the whole thing. Yeah. The other one is I'm showing you by when the parallel kinematics can be used. Like all of the example you have seen were corresponding to the serial kinematic. So here in this picture you can see there's a delta robot, right? There's a delta robot, and we know that the delta robot is a parallel kinematic, can be used to deposit the material. It is attached on the tip of the delta robot and depositing the material. Popular multi-station systems. Now I'll talk about the multi-station system. Those were only single station. I mean, only one station is there, and you mount whatever you want to mount on that. So the first multi-station system, please note, then was shape deposition manufacturing. Very early system. You can see a blur image over here. It was from 1992, I guess. In this system, what happens? There are multiple guns here, one corresponding to MIG welding, TIG welding, and they also have some innovative welding process called microcasting. They used to have laser welding. Then there's a substrate which moves between under these different stations, and then again move to the different stations like short pinning corresponding to the eliminating of the residual stresses, and then a 5-axis CNC machining center where it goes for machining operation and to eliminate to improve the surface roughness. So it's a where there is a part mounted on a pallet and moves between different stations, and that is why I said it is a multi-station system. But it was like the first multi-station system was the shape deposition manufacturing. Okay, the second, I'll not go into detail of shape deposition manufacturing, how it works, but it's a hybrid multi-station system. Okay, let me just show you the other multi-station systems. These are the multi-station systems which I developed in my PhD, and it is right now under development in IIT Bombay, where you can see that there is a rotary table and a linear axis where the part is mounted over it, and it can shuttle between different workstations. This workstation could be like deposition unit, face milling unit, stress relieving unit, inspection unit, and preheating unit. It keeps on moving between under these different stations, and the material can get deposited onto the substrate. So this is an example of multi-station, multi-axis, multi-station system, and it has already been fabricated, I guess. Yeah, the courtesies to IIT Bombay and RM Lab and AMS Bangalore, the one who is building it. I only designed it, and then after that I joined IIT Guwahati. So this is how the system looks like now. It's a big machine, and it is having 7 stations lying on the top, 1, 2, 3, 4, 5, 6, and one corresponding to the spindle, that is 7. There is a XY table right on the bottom side. It can shuttle between the different stations, and the different type of material can be deposited like face milling through the different deposition unit like TIG welding, MIG welding, laser welding. It is very much similar to what we discussed from the SGM, but yes, it is more compact and very innovative machine. Then I shall show you some of the popular robotic arm systems. Those are based on 6-axis robotic arm system, like you are seeing here. There is a robotic arm, 6-axis robotic arm. On the top of it, at the end of it, there is a welding gun attached. So such system already we have in IIT Guwahati. The video is missing. Okay, so this type of system we already have in IIT Guwahati, and now utilizing to build bigger structures. We can build the structures of around 1 meter diameter here. The 8-axis systems are also popular, like you see here. In the case of 8-axis system, there's a 6-axis robotic arm and 2 axis on the part side, like a turnitin table and rotary table, and then you can deposit material, of course, on it. The importance of having such system is like tilting the part is more easier to deposit the material than tilting the gun. Like for example, if I ask you to do the welding on the roof, then this will be nothing but the overhead welding, right? You may not prefer to do. But what if I just turn the roof upside down and then do the welding in a conventional horizontal manner? So that makes more that makes the process more easier on the welding side, right? So in a very similar fashion here also, if you use a turnitin table, then you can tilt the part and do the welding easily. This is a MIG Welding based 8-axis robotic system. As you can see here, there's a turning table and rotary table, 2 axis and 6-axis robotic arm. Yeah. Then the best according to me till now for warm systems, and it is again a multi-station system, and it utilizes the robotic arms, is LASIMM, large additive subtractive integrated modular machine. It's a very big machine, not many people know about it. It's a project of Horizon 2020 in Europe, and it is a very big machine, and they have around 7 to 8 partners in it from different domains. Like they have the partners from Cranfield universities, they are expert in the material science of the welding, and they completely know the warm process, particularly for the material science perspective. Then they have the partners from Autodesk, they are good in CAM. So I mean, it's a complete a very good team and a complete system for realizing very, very large objects. So let me just show you a video of it.
I'm involved in this project because I want to be at the front ends of technology.
So this is the system. It consisted of 2 robots and 1 turnion table, I mean tilt table. Then these 2 robots can deposit on the substrate attached with the A-axis, I mean the tilt table, and also parallel to the same, right? Parallel to the same, very much when it get tilted by 90 degree, a milling cutter is associated on a parallel kinematic robot, like I think it's a Delta robot or something. So that can do the face milling as well as the required milling operation after deposition of the process. So it's a hybrid process, and it's a multi-station system. The same robot can pick the milling cutter, as you can see, it's milling. It can pick the end milling cutter, and it can pick the inspection tool like touch probes. And it just finished the face milling. Now it will again deposit. So this is really a very big system, and that is what I think I can even conclude now in 2 minutes. The additive manufacturing is meant for, I believe, the wire arc additive manufacturing is meant for. It is meant for creating the big parts. Then only we can justify several benefits out of the process, warm, if it is used to produce really large scale objects. So I think that is it. This is a system which we are trying to build here, and I'll stop here instead of telling much about our system. Instead, I'll tell about this NPTEL course. Okay, it is over now. You cannot register on that, but the YouTube videos are available. Even for the WAM, which I try to explain to you today, it's completely available there. Whatever maths I skipped during this lecture is available on this YouTube channel of NPTEL. You can just search maybe fundamentals of additive manufacturing technologies, and then go to the playlist. There will be 30 videos corresponding to that. So I think just in 1 or 2 minutes, I'll share the lecture of WAM in the chat box, which you can refer further for any details. In case of any doubt, definitely you can write to me. My email ID is sajan.kapil@iitg.ac.in. So with this, I'll stop here, Dr. Kailash. Thank you very much.
Thank you, sir. Thank you for delivering such a nice session on wire arc additive manufacturing. It is relatively new area for all of us, because those who start working in 3D printing, they normally work on plastics, and the popular 3D printers which are available easily in the market are based on plastic, but we should more focus on metal based 3D printers. And altogether it's a new technology, wire arc additive manufacturing, and you covered the application part. You left mathematics, I know, and you talked about that also. So if somebody is interested in knowing more on this, participants can contact Kapil sir on email ID. They can watch his videos on YouTube. He's having one NPTEL course, which has been now completed, and next year we can try to join that course. So it's altogether a very challenging problem, and we need to learn more and more on metal part rather than plastic. Plastic is now old fashion for 3D printing. So now you can find the email ID in chat box also. If anybody is having any query,